Hello, my name's Nick DeMello, and we're going to start a conversation today. It's going to be a long one. It's going to take a lot of videos, and I hope you stick with it. The conversation is going to be about chemistry. So it seems like the appropriate place to start that conversation is with a video today about what is chemistry. What do we mean by chemistry? That discussion is we need to take a couple steps before that. Before we talk about chemistry, we have to talk about science. And before we have to talk about science, we need to talk about the goal, the objective of science. We need to talk about what it means to know something. We need to talk about knowledge. So let's get started with that. Like I said, we're going to focus on knowledge, and knowledge is a portion of the world around us. But there's one thing bigger than everything that we can know, and that's everything that we can imagine. Imagination is really where everything starts. Carl Sagan once said that imagination will carry us to worlds that never were, but without it, we can't go anywhere. Everything starts with imagination. And George Bernard Shaw said that imagination is the beginning of creation. You can't create something. You can't make something or build something. You can't even discover something unless you can first imagine that thing. Which is why Einstein said imagination is probably the most important thing. It's certainly more important than knowledge, because you can't know something until you can first imagine it. But not everything we can imagine is true. There's things that we can imagine that are true and that are false, and false things have value. I mean, let's not dismiss them. Romeo and Juliet wasn't truth, but it still gave us great insight. It still had great value. There's many things in literature that aren't true but are still important. There's many things that you run into every day that aren't true but are still important. The laws of the road, borders, our legal system, all of these things exist only because we agree they exist. They're not truths, but they're important, and that will have an impact on you. It's valuable to understand these things. But truth is something different. Truth is that which is consistent with reality. And truths are important. Truths matter. True walls will stop you, whether you want them to or not. True pits can trap you. True ladders, they can lift you up, and true bridges can help you cross those true pits. Truth matters. The most useful truths, though, are the ones that you're certain of, the ones that you have confidence in, the ones that true bridge that you trust to step upon will take you over that true pit. That true ladder can get you out of a true pit, but only if you have the confidence, the certainty to put your foot on each rung to go up. So truths matter most when you are certain of them, when you have confidence in them. So certainty, belief, finding truths that we can be certain of, that we can believe, this has value. This is important. It's not easy. I mean, there's a lot of things out there that are truths we haven't discovered. There's a lot of things we may have confidence in that turn out not to be true. There is a trick. There's a way to try and narrow down your focus, to find things that you can be certain of, to build confidence in that are true. And that's by using justifications. Justifications don't guarantee that you will find truth, but it's hard to justify things that are false. So if you put your weight behind things that are justifiable, then if you start to have confidence in things because of multiple justifications, it's more likely that the things that you are confident of, the things that you are certain of, will be truths. Justification can guide your certainty, and it can guide you to truths. It can help you identify things that you didn't know were true. Now, it's not enough just to have confidence in something. You can have confidence that the next spin of the roulette wheel is going to give you a red square. That doesn't mean you know red is going to come up. It just means you got a lucky guess. So without justifications, certainty even if it turns out to be truth, isn't knowledge. It's just a lucky guess. But if you build justifications, those justifications can help you identify the things that you may have been confident in that turned out not to be true, because they're not justifiable. And it can also lead you to truths that you hadn't yet identified. Justifications can help you find new truths, can grow and expand your knowledge. And this is what science does. Science is about helping us to identify, to grow our knowledge. So that's the purpose of science. I skipped a step there. But science is about understanding, studying the physical and natural world around us, and helping us to find new truths. And the domain of science is the study of that physical and natural world. This is the portion of reality that scientists focus on. This is where we have our strength. There's more out there than what we can pull into a laboratory, but this is the focus of science. This is our domain. And the way we explore things, the method of science, is based on observation. It's based on the things that we can sense, that we can see or taste or touch. Observation is more than just visual, but the things that we can observe, we can interact with in the physical and natural world, this is the domain of science. And science is a collaborative effort. If you do science just by yourself, you do it up on a mountain, you don't share that knowledge with you, it disappears when you disappear. It has no effect on the world around you. Science is, the strength of science is it is a collaboration. It's a collaboration that spans generations and crosses borders. A great example of this is a quote that was once shared by Albert Einstein. Albert Einstein said that he could only see much further than the next guy because he stood on the shoulders of giants, and he smiled when he said that. He smiled because he was stealing the quote from Sir Isaac Newton. He was borrowing that giant's shoulders. And this is a key to science. Science is not just what occurs in your head. It needs to be shared. If you can't share it, it's going to disappear when you do. But the body of science that we share, that we pass on from one generation to the next, this is the legacy of mankind. This is how we've come to change this world, change this universe, and this is how we've had our footprint on everything around us. And again, science is about the observable, the empirical, that which we can interact with. But the scientific method will help us understand that physical and natural world. Now, keys to science are, it must be reproducible. If you made an observation, even you can't be certain of that observation unless you can reproduce it. And if you want to share that observation with the next person so you can grow this shared scientific space, he needs to be able to reproduce it too. Science must be reproducible. If not, you can never have that certainty, that belief in it. It has to be testable. We need to expose our ideas. We need to be brave and put forth our ideas and allow ourselves and other people to pound on it, to explore those ideas. Science must be testable. And scientists are both the most arrogant and the most humble of people in the same breath. We're arrogant because we believe we can know the unknowable, because we can step into the unknown and gain new knowledge. But at the same time, we're humble. We're humble in that we realize we'll never know everything. Each idea that you put forth, there's going to be some falsehood in it. You have to be tentative in how you express your ideas. And you have to accept the fact that some of the ideas you're going to put forward are going to have some falsehood in them, but be brave enough to put them forth anyway. And the value of science is it's predictable. It allows us to predict the world around us. There's a lot of people who made predictions about comets, but Sir Edmund Halley, the man who predicted a comet to the month, almost the day that it would cross the sky 20 years after he died, That was amazing. And that's the value of science. Science lets you win bar bets. You can have confidence in what you claim because science will allow you to make valid, testable predictions. And that predictability, that ability to predict the universe around us is why science has allowed us to split the atom, put a man on the moon, and do other amazing things. It helps us understand the world around us. Doesn't explain everything, but the more explanatory the science is, the better it explains the world around us, the better it will be able to make predictions and grow it forward. So the best science explains what's going to happen. Not just tells us what will happen, but explains why it will happen. All right, this is science. That's the purpose and the nature of science. But what's the method? How do you get to that new knowledge using science? Let's talk about that a little bit. The method of science, well, it begins with observation. Remember, science is about the empirical. So we start with observations. Some of those observations, the taste of honey, the color of the sky. Be very careful in capturing these observations. Put down only what you can observe with your five senses. Make no interpretations of that. Capture pure observations. The best observations are quantitative measurements. They let us describe the limits of what we know and what we don't know. But we start with observation. The next step after observation is to bring your imagination to play. Try and explain those observations. Come up with a rough explanation of why this thing could possibly happen. Scientists have to be creative. Remember, these initial explanations, though, are just a first foray into the unknown. So go cautious, be tentative, but offer an explanation as to why these observations may occur. And keep your hypothesis separate from your observations. The observations are what you saw, what you measured, what you know. The hypothesis, that's the next level. It's just a possible explanation. But how do we where do we go from there? Well, the value of science is it models the world around us. It gives us a way of predicting the world around us, like a globe or a paper airplane allows us to predict things around us by modeling how they operate. The models of science are twofold. They're laws and theories. Now, the big difference between a law and a theory is a theory explains the world around you. Laws don't, but both of them model the world around you and allow you to make predictions. Now, the reason we trust scientific laws, even though they don't explain anything, is because there's never been an exception to them. It's not possible to defy gravity. We've never seen an exception to gravity. We take some liberties with that literary reference, but nobody has ever truly defied gravity. Every observation by every human being in the recorded history of mankind is consistent with the law of gravity. That's why we trust it. We've never seen an exception to it, so we have no reason to believe there's going to be an exception next week. There might be. It's not a promise. It's just a statement of history. But generation after generation after generation, hundreds and hundreds of years of observation, and you've never seen an exception to this pattern, this rule, that's a good reason to believe it. That's a good reason to trust that model. And that's what a law is. It's a statement that has no known exceptions, no recorded, reproducible exceptions in the history of all mankind. Theory is something different. Theory is even better than a law. A theory starts with that initial hypothesis, that initial explanation of what you've observed, and then we refine it. Possibly the best scientist out there was a man named Michelangelo. Have you heard about this guy? Michelangelo built beautiful models. Now, he didn't build models of the physical and natural world. Well, he did in some cases. He built models of the human body, and they were beautiful. They were pristine. Some of his statues were so remarkably lifelike. There was one, there was a model of an angel. And this statue of an angel that Michelangelo produced, it's so spectacularly lifelike, so beautiful, so perfect, that if it turned and winked at you, it'd be 2 heartbeats before you were surprised that a statue winked at you. And someone asked Michelangelo once, they said, that angel, that remarkable statue, that remarkable model that you created, how did you possibly accomplish it? He said, well, I started with a crude chunk of marble, kind of like your crude hypothesis, that vaguely resembled the truth that I saw in my vision of an angel. And then I carefully, meticulously took everything away from that granite, everything away from that hunk of rock that was inconsistent with my vision of an angel. Now, our domain isn't angels or even statues. Our domain is the physical and natural world, but we produce the models, the theories of the natural world in the same way Michelangelo did. We start with that crude approximation, that hypothesis, that crude explanation of the physical world, and then we experience the world. We put our hypothesis out, bravely put it out there for ourselves and others to explore it, and we'll find falsehoods in it. I mean, every hypothesis is going to have some falsehoods in it, but it's going to have some truth in it too. And then as we prune, as we pull away from it by experimentation and identify the falsehoods and take them out of that hypothesis, we end up with something that is richer in truth, the same way that statue was richer in the truth that Michelangelo envisioned. And as we improve that model, as we build a better and better model by removing falsehood from it, we're left with a model that is richer in truth, that is a better representation of the world around us. And eventually, if we experience that model enough, if we pull away from it enough falsehood, we end up with a theory. And that's scientific method. It starts with an observation. It starts with observing the physical world, and then setting that observation, those collected observations together, and coming up through our imagination with a possible explanation, a hypothesis. And then through our experiences, through experiments, we start plucking from that hypothesis, that initial explanation, all that we can find that's false. Scientists love to be proven wrong. Every time you prove a scientist wrong, you enrich his next theory, his next model, by having taken that falsehood from it, and you're left with a richer truth, a better model. That better model, eventually, we come to trust it, we come to rely on it. The theories that have been out there for hundreds of years, that we've pounded on and pulled so much falsehood from, probably still has a little falsehood in it, but it's so rich in truth that we call it a theory. And if we can't come up with a good explanation, but we still have that wealth of observations, we look for patterns in it. And if we find patterns without explanations, patterns that have no known exceptions, we call them the laws of science. This is the process. We start with observations, come up with our hypothesis, that crude hunk of marble, then take from it, through our experiences, more and more falsehood, until eventually we're left with a theory. And if we can't accomplish that, if we can't build a good theory from our observations, well, we can still look for patterns and produce laws. And the theories and the laws of science, these are the products of the scientific method. Now, the best part of science is we know we don't have all the answers. We don't have to have all the answers for it to work. We come up with good tools, good predictors of the world around us. From observation, we produce theories. And those theories offer us new observations. And from the new observations, we refine our theories and come up with still better ones. And no scientist will ever tell you he has all the answers. He'll never tell you any theory is perfect. It's just good enough to put a man on the moon or split an atom. But we're continually pruning and developing that through the generations. And those theories that continue to be refined. I mean, the first iPhone was fantastic. iPhone 2 was better. And as we go forward through time, through this collaborative enterprise, we're going to build still better and better theories. And the process never ends. It's never complete. We'll always be coming up with new observations and new theories. And as a result, we'll get closer and closer and closer to being able to model this world around us, this universe around us that we're trying to understand. That's the scientific process. That's the scientific method. Okay, so that's science. But I told you at the start of this, we're going to talk about chemistry. Let's focus in on chemistry. All right, this is a definition of chemistry that Webster offered us: the science of the composition, structure, properties, and reactions of matter, especially of the atomic and molecular systems. Now, if you look at the core of this, we're talking about the science of matter. That's basically what science is. It's probably the best definition. Chemistry is the science of matter. But what do we mean by matter? Do you guys know what matter is? That's an easy one. Well, it can be tricky. Matter is anything that occupies mass and, anything that has mass and occupies space. Can you think of some examples of it? I mean, wood, for example. Is wood matter? Yeah, put it to the test. Stick it underwater, see if the water gets displaced by it, if it occupies space. Put it on a scale, see if it has mass. Yeah, wood is matter. How about the water that it displaces? Yeah, you can put water on a scale. Should put it in a beaker first, but you can put water on the scale and see the mass of that water. You can also displace some water with more water. Fill up a teacup, then put some more water on top, and you'll see that water occupies space as well. How about salt? Salt was actually the third of the modern elements. I mean, we came up with quicksilver and brimstone, and then we came up with salt, and we thought salt was an element. Well, we were right about quicksilver and brimstone. That's mercury and sulfur. But salt turns out not to be an element, but it is absolutely, positively matter. How about sunlight? What do you think about sunlight? I mean, you've heard about photons, these small particles of light flying around. Well, that's a trick of the language. Photons aren't real, just like triangles aren't real, but photons and triangles are very useful nonetheless. But photons don't occupy space. They don't have matter. Sunlight is radiant energy. Not all things in the universe are matter. How about electricity? Now be careful with electricity. That's even trickier than sunlight. Electricity is the motion of electrons, and electrons are small chunks of matter. It was rather revolutionary. It was bigger than the internet when we discovered electrons, but yeah, they're small chunks of matter. But be careful, electricity is the motion of those particles. Electricity isn't matter, it's energy. It's a different form of energy than radiant energy, but it's still energy. How about heat? I mean, when you put your hand next to a fire, you can kind of feel where the heat begins and where it ends. But yeah, no, heat is energy too. Sunlight, heat, electricity. There are things out there that aren't matter. They're important, but they aren't matter. How about people? Yeah, people matter. You matter. And remember that when you're in a chemistry lab. Because chemistry lab is where we transform matter, where we change matter. There wouldn't be something in that lab unless it affected matter in some way. So pretty much every vial or flask you pick up has something in it that's explosive or flammable or volatile or mutagenic, carcinogenic, or in some other way going to affect matter. That chemistry lab is the most dangerous place you're going to be on campus. And I can justify that knowledge by showing you the insurance premiums. We pay more per square foot to insure a chemistry lab than any other place on campus. That includes the football field. Chemistry is a dangerous sport. It's a full contact science. Be very careful and never turn your back on the experiment when you're in the lab. Chemistry is dangerous. be careful with it. How about air? What do you think? Does air matter? I mean, you can't grab a hold of it. You can't put it on a scale. Well, actually you can. We can experience it. We can do an experiment. If you take an empty balloon and put it on a scale and then fill up that balloon with air and tie it, then put it back on the scale, well, the fact that you could fill that balloon shows that air occupies space, and when you put it back on the scale, you'll find that balloon's heavier. A balloon with air in it's heavier than a balloon without. So you can experience it, you can determine, and it turns out, yep, air is matter too. All right, this is the stuff that we're going to play with as we go forward. We're going to understand matter. We're going to apply science to matter. That's what chemistry is. And how are we going to do that? Well, like I said, chemistry is the science of the composition, the structure, the properties, and the reactions of matter. Do you know what I mean by composition? Composition is what something is made of. Structure is how those pieces fit together. Properties are what makes this matter different than the next matter. And reactions, that's about how you change it. Now that's an ambitious order there, to try and understand the composition, structure, properties, and reactions of a substance. How do you think we're going to answer those questions? Well, let me put it to you another way. If I asked you to understand a clock, if I asked you what that clock is made of, how the pieces fit together, what makes it unique, and how you can change it, what would you do to that clock? Come on, be honest. You know what you would do to that clock. If you wanted to understand how clocks work, you would take them apart. That's what we're going to do. But we're going to understand all matter. We're going to explore different types of matter. We're not going to figure out how clocks work. We're going to figure out how rocks work. But we're going to do it the same way. We're going to take that rock and we're going to break it into smaller pieces. And then we're going to take those pieces and break them down still again. We're going to break it down to pebbles. We're going to break it down to gravel. We're going to break it down to dust. And we're going to keep breaking it down till we get to the smallest particles of matter that we know about. Well, for the purposes of this class. We're going to break it down to atoms and molecules. And that's how chemists explore and understand the world around them, by understanding those smallest pieces, by exploring, experiencing, working with the atoms and molecules that make up the matter around us. Now, we're just getting started on this discussion, but to give you a taste of what's coming forward, we're going to explore different types of matter. And when I hand you some new matter in the lab, you're going to look at me and say, geez, this is just like the same stuff I looked at before. It's a white powder. You're going to get bored with white powders real fast. But as you understand the particles that make it up, you'll understand why this matter is different than the next. Some of that white powder will dissolve in water. Others will float in water. Some will turn pink when you drop it in water. Some will burn when you drop it in water. Some will freeze the water when you drop it in. And some white powders will turn into water. That's the chemist's best trick. And you're going to understand as you go forward how all this is accomplished by understanding the atoms and the molecules that make up that matter. At least that's what we're going to try to do. I mean, at the end of the day, I can lead you up this mountain. I can show you the best way to put your foot, where to trust to put your foot as you climb that mountain, what paths to avoid, what might be an easier place to climb. But I can't put certainty into your mind. The best I can do is offer you justifications and allow you to build that certainty in your own mind, build that knowledge on your own. I'm going to try and help you experience the world around you through the eyes of a chemist, and I hope you're going to come to knowledge of chemistry. Well, if you've got any questions, just shoot me an email, and I'm looking forward to our next discussion. Thanks, and I'll talk to you soon.